Okay, these are some examples that should help you handle the homework okay. This is example 2 from the text, and I just kind of filled in some of the steps. They skipped steps a lot, so you can take a look at that example. I'll also say that you should look at example 3 and 4, although I won't go over those. They're explained pretty well, the concept of what to do in certain instances, so be aware of that. Again, they skip a lot of steps, and you can work those out if you want and fill in the steps, although some they do with a calculator. But just try to follow the steps, and they do, again, cover how you handle certain situations. But the examples I'll give you be a little bit more practical as far as what you're going to have to do for your homework. So we want to find the exact length of the curve, and this was the curve, y equals 4 times the square root of 2 over 3, x to the 3 halves, a minus 1 for this interval. So the first thing from 0 to 1, so the first thing we're going to do is going to find dy dx, because that's going to be in our formula. And again, on this interval, I think this function is CC2, so that's no problem. So our mean value theorem will apply. It's got to be continuous on the closed interval and differentiable on the open interval, and I don't think we're going to have any problems on the open interval. We would have, might have, we're okay on the open interval, yes. Okay. And we take the derivative, and if we take the derivative, that's going to be 3 halves and times this, and the x to the 1 half, and the 1 goes away, which is 2 times the square root of 2 times x to the 1 half. And this is also has to be continuous on the open interval. I'm sorry, on the closed interval, 0 to 1. Okay, so the derivative has to be continuous, so it is indeed a smooth curve. So all we have to do is apply the formula. So remember the arc length will be from 0 to 1, the interval from 0 to 1 of this 1 plus dy dx squared dx. And we already figured out dy dx. So we just substitute in 1 plus 2 times the square root of 2 times x to the 1 half squared dx. And then we square that, that's going to be 2 squared is 4, square root of 2 squared is 2, 2 times 4 is 8, and then if I square that, that's going to be first power. And I can write this as a exponential power, and I'm going to use a u to the n du form. Okay, 1 plus 8x to the 1 half. Okay, so it looks like if we call this u, what's my du going to be? If my u is 1 plus x to the, 1 plus 8x. And I could jot this down, although right below, we don't want to have to use a whole u substitution, but if we let u equal 1 plus 8x, then what would du be? Du would equal 8 dx. Okay? So you could jot that down. I'm not doing the whole u substitution, but what we need here is we need a du, we need an 8 dx if this is without actually making the substitution. But you know what you need? You need an 8 dx here. So over here what I did was I put the 8 here. But I can't just multiply by 8. I have to multiply by 1. So 8 over 8 is 1, so I put the 1 over 8 in the front. Now I have it as u to the n du. And my u was 1 plus 8x. And my n is 1 half. And my du is 8 dx. So you can just write that down there, and then you know you're using u substitution, although we're not actually putting a u in. Okay? And then if I take the antiderivative of this, I add 1. So that's going to be 3 halves, and I divide by 3 halves or multiply by 2/3. And I'm going to evaluate that from 0 to 1 using the fundamental theorem of calculus. Again, this is your f of b minus your f of a from the fundamental theorem of calculus. All right? So this is going to be, this is 2 goes in there 4 times 4 times is 12, 1/12. And we're evaluating that from 0 to 1. So if I put 1 in here, that's my f of b. And if I put 0 in there, that's my f of a. AB. Okay, and then 8 times 1 is 1. That's 9. So that's 9 to the 3 halves minus 1 plus 0 is 1 to the 3 halves. It's going to be 1/12, and 9 to the 3 halves is what? 27. 1 to 3 halves is 1. That's 26 over 12. 1/12. And that's 13 over 6. So those are all the details. Okay. And I got a couple more examples because I did a couple problems by mistake, so they'll be good examples. Okay, this is number 1. Jumped right into this, so this is number 1 from your homework, and you have to do 3, so this will give you a good indication of what you do. Okay, y equals x squared. So we know that this is CC do no problem on this interval. And then we also know that the derivative, if I take the derivative of this dy dx 2x, that's also continuous. So it is a smooth curve, that's no problem. So we just use our formula here and substitute in the integral from -1 to 2 of 1 plus 2x squared dx. And this is going to be, again, just this integral from a -1 to 2 of 1 plus 4x squared dx. And a lot of these you are going to have, they're not going to work out real nice unless they tell you to do them analytically, and check it with a calculator. So these first few you can do with a calculator. I think 3, 6, and 9 you'll work with a calculator. Because lots of times in these problems it's hard to come up with the ones that work real nice. Okay, so this was actually the integral they wanted you to set up. There were 3 parts of these problems. A was set up the integral. B, sketch a curve. Well, that's no problem to sketch that curve on that interval. So we're going to actually find the length of this curve. Okay? Or if it was a piece of wire, if we stretch it straight out, what would the measurement be? And then we're just going to use our calculator, our Math 9. Okay, this is the Math 9. It actually showed how you would actually put it in the square root and then parentheses that function, which is straightforward. X is my integral, or my variable of integration, and then from -1 to 2, and we got this. Okay, so no problem. And let's see if we can get one more in. This was number 11, and they wanted you to do this analytically, so those are a little bit more fun. So this is an extra problem. I did it by mistake, so I just finished it up because they're not too hard. So y was this function, the 1/3 x squared plus 2 to the 3/2 from 0 to 3. So we want to find dy dx. And that's just going to be 3/2 times 1/3 to the 1/2 times the derivative, which is 2x. And these cancel, these 2's cancel, so this is my dy dx. And I just put it in my formula. No problem, this is going to be continuous. That's not a problem. I don't see any discontinuities there. Over this domain 0 to 3, and no problems here, so we're in good shape. Okay, so we just substituted in, and you can see how we did that. X squared plus 2 to the 1/2 times x squared, and we end up with 1, and then this just becomes the 1/2 squared, that just becomes x squared plus 2, and then times x squared. And then we multiply everything out here, we get x plus x to the 4th plus 2x, and we end up with this. Now this is a good example because now this is just going to be a binomial square. So when you're doing these analytical problems, you're going to work them out without a calculator. You're going to have to get some perfect squares in there. I think they give you some hints in some of these. But if I write this as x squared plus 1 squared, by factoring that as a trinomial square, I can see that. And see how easy it is now to take the square root of that is just this. Okay. So you have to do some algebraic manipulation to get some perfect squares in these so you can actually take the antiderivative without using a calculator. And now we've got this in a nice simple polynomial. So that's going to be x to the 3rd over 3 plus x, and evaluate that from 0 to 3. So if I put 3 in here, I get 27 over 3 plus 3, and if I put 0, I get 0, so my 0 part disappears, so I don't have to worry about this bottom part. And then that's going to be 9 plus 3 is 12. So nothing too difficult here. Okay? So I hope that helps. So you should be able to handle the homework pretty easily.